Hi, I'm going to cover question 3 from Friday's tutorial, which I didn't have a chance to cover in class. So we've been given the free body diagram here that's been presented to you, and we've got our restraints at points A, B, C, D, and E. We've been given our live and dead loads, and we've been asked to select the minimum mass universal beam of grade 350. So the first thing I'm going to do is actually find my design factored load. It's going to be the maximum of 1.35 times the dead load, or the 1.2 times the dead load plus the 1.5 times the live load. If you solve this, it comes out to be 13.5 and 30 kilonewtons per meter. Maximum would be 30. Now that we've got our design factored load, we need to find the reaction forces at B and E, particularly because we want to draw our bending moment diagram, and based on our bending moment diagram, we need to find our factor alpha M. So the first thing I'm going to draw is my shear force diagram. And we need to find our alpha M for segment AB. So I'm going to use the alpha M formula with the 1.7 times the M at the middle, and then add 1/3 of the lengths. So I need to, if you calculate, you'll get your shear forces at these points to be equal to 22.5, 45, and then 67.5. Basically, you know that this value is going to be a half of 0 and 90, and then a half of 45 would be 22.5, and then the mid value between 90 and 45 would be 67.5. We know that when the shear force is 0, it should be a point where you have your maximum bending moment, and so we need to calculate this distance x. So x, using similar triangles. you get 4.14 meters. Now we're going to draw the bending moment diagram, and if you remember from your first year engineering mechanics, your mechanics of solids and structural analysis, your bending moment should look like this. So the maximum bending moment at B is 135 kilonewton meters, and then at a point 4.14 meters away from point B, the maximum bending moment is actually 122.508 kilonewton meters. So if you find the area of these triangles, this triangle, of that triangle, and this, you can get your bending moments at those points. So you should get 33.75 in the middle, 0.4375, and then 75.9375. The other thing is that when we got our moments, we're going to consider segments A, B, and B and CD. Remember in class when I mentioned that it's FL or LL that's critical? And if they're critical, then we have to start considering lengths. So if lengths are longer, then it's going to be more critical because your moment is inversely proportional to your L. A larger length means it's a smaller MO, and then your M star has to be less than your MO. So the region with a longer length would be critical when you have segments having restraints, these restraints. So we're going to consider segment BE. There are two ways of doing finding the alpha M for BE. I'm going to use table 5.6.1. if you do the alpha m using the formula from clause 5.6.1.1, you'd get 1.43, and you can see they're not too different, so you can use either. We're going to look at segment CD. We know it's going to be critical, particularly because we've got bases F and L, CDs L and L, and then the length of CD is longer, and so it's going to be more critical. Because if you have a longer length, you have a smaller moment, your reference buckling moment. So for CD, from table 5.6.3, you'd get your KT factor equal to 1.0 because your L's 3000 millimeters. Table 5.6.32, get your KL factor equal 1.4, and then from table 3.3, your KR factor is going to be equal to 1.0. So if you want to find your LE, which is KT L, you should get a factored length of 4,200 millimeters. Now that we've got our lengths, we need to find our alpha M for segment CD. So we need to use clause 5.6.1.1. So we need to find our moments. So I'm going to find a general expression in terms of x, your moment. So that's that. Cut a section along your given B. 0.7 omega star, and then we have NB acting at 3 meters away from our left end, and then I'm going to take my X, my reference starting from the left edge. So you take the moment about XX bar, what you'd get is mx plus 30 on 2 squared. 30 is your factored, your design load, your omega star. 214.3 is NB, so you get that equals 0. So you have a general expression for finding mx, which is 204.3 x minus 3 minus 15x squared. So if you want to find your moment at point 2, which is 1/3 of the length, 5.75, you should get 93.3875 kilonewton meters. Your moment at 6.5, which is the middle, should get 116.3 kilonewton meters, and at 7.25 you should get 122.3375 kilonewton meters. Now we're going to find our alpha m. This is going to be our m star m. This is going to be equal to m3 star, and then this is going to be equal to m2 star. My bad. That's 4. And then mm star is going to be equal to 122.508. And that's actually the moment from here. So we find our alpha m. To 3.3875 squared. You should get an alpha m of 1.08. Now we need to assume our alpha s. Alphas of 0.75 and 0.8 are good assumptions when you have a steel grade of 350. So the first thing we do is initial sizing. Your SX with an M star, phi alpha M, alpha S, alpha Y. And one important thing is that check, oh my god. So the value that you assume must make sure that the multiplication of your factors is less than 1. Your assumed factor. Else you need to change your assumption. So you get your SX is actually going to be greater than or equal to 122.308 10 to the power 6 because we want Newton millimeters. Phi is 0.9, alpha m is 1.8, alpha s is 0.8, and then your tensile stress or the yield stress is actually 350 because that's the given grade. So you get 450.1 times 10 to the power 3 millimeters cubed. Now we're going to select our member. So from One Steel catalog, choose 310 UB 32. So we're going to pick out the data from the catalog, that is the thickness of the web, your D1, which is exclusive of your flange thicknesses, I think, or the depths. Get 282. The total depth of the section is 298 millimeters. Your Fy should be the minimum of the yield strengths or the stresses of your flange and your web, which is a section modulus and then W, which is 9.29 10 to the power 10 millimeters to the 6. Second moment of area, then your J. So these are the details that you pick up from your catalog. So we're going to find the compact section moment. That's section modulus for your elastic section times the U stress. Comes up to be 60.3 kilonewton meters. Now we need to find the effective length. We've already done that. So we need to find our reference buckling moment, M0, which is going to require our alpha S. So we need to find alpha S first, actually. No, we can do that later. Anyhow, so in your solutions, they haven't given you the formula for finding the reference buckling moment. I'm actually finding it in my book. Got it? It's going to be pi squared EIY divided by LE squared. Remember, we found LE, your effective length, and it's 4,200. JJ. Your J values given to be 80,000 megapascals. E for steel is 2 times 10 to the power 5 megapascals, and everything else is known or either given. So you get your reference buckling moment to be equal to 92.5 kilonewton meters. Now we need to find our MB, and to find MB we need alpha S. Although we assumed an alpha S, we have to now recalculate based on our reference buckling moment and our section moment, compact section moment. 3 minus, there should be a squared somewhere. No, it's not squared. Sorry. I think in class I put a square up here. That's actually wrong. It's not squared. Got mixed up with one of the other courses. So your alpha S is 0.2. So we need to find phi MB, which is phi alpha S alpha M times your MS, sorry. 9. Comes up to be 68.0 kilonewton meters. And your phi MB is actually not greater than your M star, which is 122.5 kilonewton meters. Therefore, not okay. So we need to choose a new member. So this time we're going to pick 360 UB 44.7. These are the details from one step catalog. Excuse me. So these are the details of your 360 UB 44.7. And now we're going to do the calculations that we did for the other universal beam, finding our our MS on per section moment, which comes out to be 274.3 kilonewton meters. We're going to find our M0. I'm not going to copy the formula again. Basically, it's this formula. The only values that will change are IW, J, IY. That's pretty much it. These are the only three values that are going to change. You should get a reference buckling moment of 189 kilonewton meters. Your alpha S, same formula, comes out to be 0.485. And now your phi MB is equal to phi M S 9.485 times alpha M's the same, 1.08, comes up to be 129.3 kilonewton meters. And that is larger than our design moment, 2.5 kilo. Therefore, okay. Now we know that the most critical section is CD because it is LL, and then the length of this subsegment is the largest. However, in your solutions, they also want you to do a check for segment AB, which is fully restrained at both ends. And so, because your solutions want me to do that, I will have to do that. So we're going to check AB. So KT is going to be equal to 1.0, particularly because it's FF. L as well. And then for KR, you take the maximum value because it is fully restrained. Now we calculate our LE, your effective length, will also come out to be 4,200 millimeters. So if you put it in your reference buckling moment formula, you wouldn't be different. It would still be 189 kilonewton meters, particularly because your LE was the same for segment CD and AB. So if your reference buckling moment is the same and your section moment capacity remains the same, your alpha S is also unchanged. So your phi MB is going to be the same. It's going to be 129.3. I am sorry, it's not going to be the same. Reason why: alpha M is not the same. We haven't found our alpha M for subsegment AB, so if you have a look for that, we're going to do it by using clause 5.6.1 or 2.1, 5.6.1.1. So 1.7 times 135 is going to be square rooted by 8.33 and then 75. 9375. These values are actually coming from here. They're these guys. So should come out to be 2.75. Remember, our maximum alpha M value is 2.5. Therefore, set alpha M 2.5. Now that we got that, so if you find your phi MB, it's going to be phi alpha M alpha S MS. It comes up to be 299 kilonewton meters, which is of course evidently bigger than your design moment, 135 kilonewton meters. Remember, your 135 is this, is for this guy. It's specific for segment AB. So it's okay. So it's working because it's larger. So UB, what's that guy? UB 360, 44.7 is selected. Now the important thing that we're going to do is check for shear. Now to check for shear, the first thing we check for is the shear capacity. From our shear force diagram, we got our V star max to be equal 124.3 kilonewtons. This is this guy, it's our maximum, and that's our design shear. And first thing is shear capacity, which is VW, actually 0.6 times AW FY, where your AW is equal to D1 times TW, which is copying, that should be 352. D. No, they didn't find the area. You just do 6.9. So your VW is going to be equal to 0.6 times 352 times 6.9 multiplied by 360. 524 kilonewtons. Now we need to find our nominal shear buckling capacity. Denoted by alpha V. So it's like your alpha M and your alpha S. So that's 82 squared. So plug in your numbers. Put in 352. Put in 6.9. Put in 360. It should come out to be equal to 2.0, which is not less than 1.0. Therefore, your shear yield capacity is more critical. Which means that VV equal VU equals VW. So if you find your phi VV, remember your phi value for shear is not 0.9. It's actually it should be 0.75. They didn't do the calculation over here. They just gave you your value to be 471.6 kilonewtons. And in my solutions as well, I just wrote 471.6. I did not write what my phi value is, but I'm just put in, try subbing in 0.9 and 0.75. It should be one of them. However, your phi VV is actually way larger than your V star max of 124.3 kilonewtons, therefore okay. So the other thing that we need to check for is shear flexure, that's shear caused by bending interaction. That's the formula. And that's what's the moment, 274.3 comes out to be 185.1 kilonewton meters, which is larger than 135 kilonewton meters. Therefore, okay. That's how you check for your shear, and that's the end of this example. Thank you so much for paying attention.